Welcome to Maths with EJD. In this video, we're talking about Cholesky decomposition under numerical analysis, especially talking about solving systems of linear equations. So generally speaking, talking about solutions to systems of linear equations. Broadly speaking, algebraic equations, right? So such solutions have two key methods. Uh, we have one class of methods called direct methods, and then we have the iterative methods. So under the direct methods, we have seen Gaussian elimination. We have seen LU decomposition. So in this video, we'll be talking about Cholesky decomposition. Cholesky decomposition. So future videos will make us come in contact with Jacobi method under iterative. We have Jacobi method. Then we have Gauss-Seidel method. And then we have successive over relaxation, SOR for short. So our focus here tends to Cholesky decomposition. So, in LU decomposition, right, we break down the coefficient matrix into a product of lower and upper triangular matrices. But in the case of Cholesky decomposition, it's a bit different, and that's what we want to see now. So Cholesky decomposition is a direct method that factorizes a symmetric, very important, the matrix has to be symmetric, a symmetric positive definite matrix, a symmetric positive definite matrix A into the product of a lower triangular matrix L. That means that everything above the principal diagonal will be 0, and its transpose that is we want the coefficient of the coefficient matrix of our system to be factorized into a lower triangular matrix multiplied by its transpose. So, and that is for efficient solution of linear systems. Efficient solution of linear systems. So for LU decomposition, right, A is equal to LU, but for Cholesky decomposition, A is equal to L multiplied by L transpose, basically. So, as usual, the problem we've been solving was, so I want to use the same, all the methods on the same problem so we can see where the differences actually lie. So let's look at an example. So solve x plus 2y plus 3z equals 9, and 2x plus 5y plus 6z equals 18, then 3x plus 6y plus 14z equals 30. That's the problem we need to solve using Cholesky factorize Cholesky decomposition. Cholesky decomposition. So the first thing we need to establish is that is if the matrix is symmetric. But before we even do that, let's extract the matrix itself. Solution. So the coefficient matrix, we see that it is the same thing as 1, 2, 3, then 2, 5, 6, and 3, 6, 14. Okay, and then we have the vector of solutions, or vector of the variables x, y, z, and then we have the right hand side b, which is 9, 18, 30. So the question is, we need to check. Check if A is suitable for Cholesky decomposition. That's the first thing we do. And the first check is about symmetricity, symmetricity. So you have to check, of course, you know, check A transpose A, that's 1, 2, 3. So the row becomes column. That's what the transpose is like. So row 1 becomes column 1. So we have 1, 2, 3 here. Then row 2 is 2, 5, 6. It becomes column 2. That's 2, 5, 6. Row 3 becomes row 3 is 3, 6, 14. It becomes column 3. That is 3, 6, 14. Now, is it still the same? Yes. Okay, so we say since A is equal to A transpose, since A is equal to A transpose, A is symmetric. That's the first check done. Okay. So the second check is about positive definiteness. Positive definiteness. Now that's a bit trickier. So for positive definiteness, we want to see, so we have, it's in different layers. So we have to take the 1 by 1 matrix, 2 by 2 matrix, and 3 by 3 matrix, the determinants for that. So first of all, we need to do determinant of A, that is 1 by 1. In that case, now that's just determinant of A 1 by 1. That means, so for 1 by 1, we have only this. Oh, okay. I guess let me write it out again. Let me just write out A generally. So A is 1, 2, 3, 2, 5, 6, then 3, 6, 14. So 1 by 1 is just this. 2 by 2 will grow to this. Okay. 1 by 1 is this, right? Let me do it this way. This is, if you are doing 1 by 1, this is it. For 2 by 2, this is it. And for 3 by 3, that's everything. 3 by 3 is everything. So you have to find the determinants at all those levels. So first of all, we have, let me do green. So determinant of A 1 by 1, that is determinant of 1, which is 1, and that is greater than 0. That is positive, okay? Next, you go determinant 2 by 2. Okay, let me follow the colors. So 2 by 2, the determinant of A 2 by 2, that is determinant of 1, 2, 2, 5. 1, 2, 2, 5. So that is 5 times 1. That's 5 times 1. Minus, this is 5 times 1 minus 2 times 2. So that is 5 minus 4. That is 1, which is still greater than 0. That's still positive. Then we now go for determinant 3 by 3. 1, 2, 3, 2, 5, 6. So determinant of A 3 by 3. So this is determinant of 1, 2, 3, 2, 5, 6. 3, 6, 14, 3, 6, 14. So we need to find this determinant, and the way to just go about that is just assign values. This is plus, minus, plus. Okay, so that means we have plus 1 into the determinant of, if you cross this and cross this, okay, we have 5, 6, 6, 14 down there. 5, 6, 6, 14. So next is minus 2. You know, this minus 2 now. So we have that minus 2 into, then cross the column, cross the row. We have 2, 6, 3, 14. 2, 6, 3, 14. That's 2, 6, 3, 14. That's if you cross this column and this row. You have 2, 6, 3, 14. Finally, we have plus 3. This is plus 3 now. Okay. Then if you cross the column, the row and the column, we have 2, 5, 3, 6. 2, 5, 3, 6. This is 2, 5, 3, 6. Okay. So we can go ahead now and do the determinants, right? So determinant A, 3 by 3, that's equal to 1 into 5 times 14, that's 70, minus 36, minus 2 into 14 times 2, that's 28, minus 18, that's 3 times 6, right? Then plus 3 into 2 times 6 is 12, 12 minus 15, okay? 2 times 6, 12, 3 times 5, 15. So we now have 1 into 70 minus 36 is 24, I believe. No, that's 34. 34 minus 2 into 28 minus 18 is 10, plus 3 into 12 minus 15, that's minus 3, right? Yeah, minus 3. So we have 34 minus 20 minus 9. So that is 34. That is 34 minus 20 is 14. 14 minus 9 is 5. That is greater than 0. That is still positive. Okay. So we can conclude then that since determinants A 1 by 1, determinant A 2 by 2, and determinant A 3 by 3 are all positive, all right, then A is positive definite. It's positive definite. It's positive definite. And that goes. So we can then say that since A is both symmetric and positive definite, then it is suitable for Cholesky decomposition. So if it is not suitable for Cholesky decomposition, don't even bother, because it will break down. All right, now that you have concluded that it is okay for Cholesky decomposition, so let's go ahead and do Cholesky. So here now, we need A equals LLT, where L is equal to, just like what we had before, L11, 0, 0. So in this case, just unlike what we did for LU decomposition, we don't have 1 on the principal diagonal by choice. So L11, L21, L22, 0, L31, L32, L33, like this. So this is it. So automatically L transpose will just be you transposing this, right? Row 1 becomes column 1. So you have L11, L11, 0, 0, L11, 0, 0. Then row 2 becomes column 2. That's L21, L22. Row 2 becomes column 2, right? L21, L22, 0. And row 3 becomes column 3. That's L31, L32, L33. Okay. So at the end of the day, we want A to be equal to all that, right? So A equals LL transpose. Oh, I think this should be transpose, hanging up, not down like this. Okay. So next, we now have A. A is 1, 2, 3, 2, 5, 6. So on this side now we have so we know, okay, or let's just do LL transpose first before we compare with A. So LL transpose is equal to, so just like I like to do, so I have L1100, then L1100, then L1100. Next, we have L21, L22, 0, L21, L22, 0, then L21, L22, 0. Lastly, we have L31, L32, L33, and L31, L32, L33. Then lastly, L31, L32, L33. So if you can now invert the other side on it. So row 1 is L1100. So we have L1100, L1100, L1100. Then next we have L21, L220. So L21, L220, L21, L220, L21, L220. Then lastly, we have L31, L32, L33. So L31, L32, L33, L21, I mean L31, L31, L32, L33, and L231, L32, L33. So not to waste time, we need A equals LL transpose, right? So A already is 1, 2, 3, 2, 5, 6, 3, 6, 14. And that is equal to, so carefully work this out. So this is just L11 squared. This is L11 squared. So the next one is L11, L21, L11, L21 plus L22, I believe. So this is, okay, now that's just 0, right? So that's just L11, L21, L11, L21. So then lastly, we have L11, L31, L11, L31 up there. Then comment, that's for this now, this first line. So next we have L11, L21. Oh, okay, interesting. L11, L21, L11, L21 here. Then next we have L21 squared. We have L21, L21 squared, and L22 squared. That's this now. Then here we have L31, I mean L21, L31 plus L22, L32. That's this. Then coming down here, we have L11, L31. That's just like this. Then here we have L21, L31, okay, plus L22, L32. Okay, that's just like this one. So finally, we have L31 squared plus L32 squared plus L33 squared. Okay, so we see some symmetricity here, of course, because the original matrix 2 is symmetric. So we can begin to get the values. So let's start with L1 squared. So you see that L1 squared is equal to 1. That's this and this. So that implies that L11 is simply 1. So we're done with that. Then next, we have, so L L11, L21 is equal to 2. Just like this, L11, L21 is also equal to 2. So that's taken care of. So I mean, we basically need how many things do we need? We need just L11, L21, L31, L22, L3. We need just 6 things. So we've got 1, So L11, L21. So L11, L21 is equal to 2. So that implies L11 is 1 times L21 equals 2. So that implies that L21 is equal to 2. Settled. Then we go for, what else do we need? We can go for this next one. So L11, L31, which is the same as this. L11, L31, that's 3. So L11, L31 is 3. L11, L31, that's equal to 3. And we know L11 is 1. That's times L31 equals 3. So that implies that L31 is equal to 3. So we have that sorted. Then we have, do we have L21 already? Yeah, we have L21. So, okay, guess I need to choose another marker. So L21 squared, L22 squared is 5. So L21 squared, L22 squared is equal to 5. That implies L21 already is 2. So we have 2 squared, L22 squared, and that is equal to 5, right? Yep, because L21 is 2. Okay. Yeah. So that means we have 4L22 squared equals 5. So L22 squared is equal to 5 over 4. So L22 is square root of 5 over 4. That is root 5 over 4. Root 5 over 2. Root 5 over 2. Like this. Then what else? So we have L22 equals root 5 all over 2. Then, okay, we have, okay, this and this are the same. This and these are the same. And they're both equal to 6. Equal to 6. So L21, L31, L21, L31 plus L22, L32, L22, L32, L22, L32, and that is equal to 6, right? Yeah, that's 6. So L21, we already have L21 to be 2 times L31. Do we know L31 already? L31 is 3. L22, we just got that to be root 5 over 2 times L32, which I think we don't know yet. I think so. So L32 is what we are looking for now. So L32. So this is 6 plus 5, root 5 over 2, L32 equals 6. So if we subtract, so we have root 5 over 2, L32 is equal to 6 minus 6, that's 0. So L32 is simply 0. Nice answer, I think. Then lastly, we have this, which is equal to 14. So L31 squared, L32 squared, L33 squared. So L31 squared plus L32 squared plus L33 squared is equal to 14. Okay. So what is L31? L31 is 3 squared. L32, I think L32 is just what we got now. L32 is 0 squared. So we can get L33 squared, which is 14. So this is 9 plus 0 plus L33 squared, which is 14. So L33 squared is equal to 14 minus 9, that's 5. So L33 is equal to root 5. And that is a third. We cannot get the perfect square root of that. So we can then have our L. Therefore, L is equal to, so L1100, L1100. So L11 is 1. So that is 100. Then L21 L21, L220, L21 as 2 root 5 over 20, 2 root 5 over 20. So, I share 2 L21, L220. So that's 2 root 5 over 2, 0. And lastly, we have L31, L32, L33. So L31, L31 L31 is 3, thankfully. L32 is 0, and L33 is root 5. Okay, so that is the lower triangular matrix that we can get from that coefficient matrix. Now that we have all this, the next thing we want to do is so we now have to solve the system. We now solve AX equals B. Okay, we want to solve that system AX equals B. But what we have to do first of all is we do Ly equals B. We solve for Y, forward substitution. Then we now solve LT equals X, backward substitution, and we get our answer. So next step, we solve Ly equals B. So we already know our L, right? So that's 1, 0, 0, 2 root 5 over 2, 0, then 3, 0 root 5, 3, 0 root 5, and Y, right? Now Y now is Y1, Y2, Y3 like before, and that is equal to B. That's the B we started with, 9, 18, 30, 9, 18, 30. Then, I mean, we are used to doing this already. Should I just do it still? So this is Y1, Y2, Y3, then Y1, Y2, Y3, and again, Y1, Y2, Y3. So put it over this. This 1, 0, 0. This is 2 root 5 over 2, 0, and 3, 0 root 5, 3, 0 root 5. All this is equal to 9, 18, 30. So that means for this now, this is 0, this is 0. So we have Y1 equals 9. So that is forward substitution, right? It says we solve this using forward substitution. So you get Y1 first and keep going. What forward substitution? Okay, so Y1 is 9 already. So next we have this is 0. So we have 2Y1 plus root 5 over 2Y2, and that is equal to 18. So all this is equal to 18. So we have Y1 already. That's 2 times 9 plus root 5 over 2 equals Y2, and that is 18. So root 5 over 2 Y2 is equal to, this is 18, right? That's 18 plus 18. So in essence, we are saying that if you subtract it from here, so we have root 5 over 2y2 equals 0. So y2 is simply 0. Done. Then lastly, we have this now. So this is 0 for sure. So we have 3y1 plus 0, because y2 times 0 is 0. Then root 5y3 equals 30. Root 5 y3, that's 30. But we know y1 is 9, so that's 3 times 9 plus root 5 y3, and that's 30. So this is 27 plus root 5 y3 equals 30. So that, I mean, if you subtract this, we have root 5 y3 equals 3. So that y3 is equal to 3 over root 5. We can rationalize that. So y3 is 3 root 5 over 5. Okay, so we have, so therefore y is equal to y1 9, y2 0, and y3 is 3 root 5 over 5. So that's second to the last step. So the last step is to solve. So we now solve for, so we solve L transpose X equals the Y we just got now for X by backward substitution. Backward substitution. So so remember L transpose X now. That's just us transposing the L we got. So this is L, right? So L transpose is row 1 is column 1 now. So L transpose is 1 0 0. Row 1, which was 1 0 0, is now column 1 here. Then we have 2 root 5 over 2 0. So that is 2 root 5 over 2 0. And last row, which is 3 0 root 5, is now last column. That's 3 0 root 5. That's L transpose. So to solve for X now, so we have, of course, we need X. X now is X, Y, Z that we started with. And we have Y. So Y is that which we just got. No, we just got, I don't need to repeat that, right? 903 root 5 over 5. So we have, so L transpose X equals Y is such that we have 1, 2, 3, 0 root 5 over 2, 0, 0, 0 root 5 equals X, Y, Z equals the Y we just got, 903 root 5 over 5, 903 root 5 over 5, so that we can now have the same thing I've been doing. So we have X, Y, Z, X, Y, Z, and X, Y, Z. Now it's backward substitution. So you get Z first and then you walk it forward. So this is 1, 2, 3. This is 0 root 5 over 2. Then 0. Then next row is 0, 0 root 5. So 0, 0 root 5. And that is equal to Y. That's 9, 0, 3 root 5 over 5. Okay. So that means that you have X plus Y. X plus, yes, I want to go this way. X plus 2Y plus 3Z equals 9. Then next, we have, this is 0, this is 0. That is root 5 over 2Y equals 0. Then, of course, from here, we can easily get that Y is already 0 like that. So multiply both sides by 2 over root 5. You just get 0. So Y is settled. This is 0, 0 like this. And then you have Z root 5. So Z root 5 equals 3 root 5 over 5. 3 root 5 over 5. So that means that if you cancel root 5 on both sides, so Z is 3 over 5. So we have this. So we now need only X to go. So from X plus 2Y plus 3Z equals 9. So we have X plus 2, Y is 0, 3 into 3 over 5, just like we've been getting. And this is equal to 9. From other methods, that is. So this is gone. So X plus 9 over 5 is equal to 9. If you multiply 3 by 5, you have 5X plus 9 equals 45. So that means that 5X is equal to 45 minus 9. So 5X equals 36. So that X is 36 over 5. So we can conclude that therefore X is 36 over 5, which is the same thing as 7.2. It's the same thing as 7.2. Y is equal to 0. And Z is Z is 3 over 5. which is the same thing as 0.6. And that is the end of Cholesky decomposition. So interesting, pretty long, but you can follow through. Thanks for listening up till this point. For a practice question, you can take this. Okay, practice question. So, practice question, we have solve u plus 2v plus 3w equals 1, 2u plus 5v plus 6w equals 3, plus 6w equals 3, 6w equals 3, then 3u plus 6v plus 14w equals -2. Thank you for listening. If you have subscribed, thank you so much. If you haven't, do that right away. Hit the notification bell so you can always get alerted each time a new video is released. Then comment, let me know how helpful this video is, and let me know if there's a problem you'd like me to solve, a topic you'd like me to teach. Like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.